Welcome back. In the next part of this section, we'll be talking about horizontal asymptotes, another feature that we'll have in our rational functions. So if you're thinking back to the graphing of polynomial functions in 5.3, one of the things that we talked about was the end behavior. And for polynomial functions, they were either going to be going up forever on the far right or going down forever on the far right. And same thing happening at the far left, either going up forever or down forever. Things are a little bit different with rational functions, however, because it may be the case that instead of going up forever or down forever, that our graph will taper off at the far left and the far right to some sort of horizontal line, so that we may be wiggling around in the middle for a while, but then eventually taper off to a horizontal line on the far left and also on the far right. That line, we would call that a horizontal asymptote. Now, one thing that's true for rational functions is that if you have a horizontal asymptote, you'll have it on both sides of your graph, at the far left and at the far right, and it's going to be the same horizontal asymptote on the far left and also the far right. That's not going to be true for every function we see in this course. We're going to see for exponential functions, they only have asymptotes on one side of their graph and not the other. We'll also see there's some other functions that have two different horizontal asymptotes, one on one side of the graph and a different one on the other side. But for our rational functions, the story is a little bit simpler. Either we're going to have the same horizontal asymptote on both sides, or we won't have any horizontal asymptote on either side. And as far as the decision-making process, it really just comes down to looking at the degree of the top and the degree of the bottom. If the top and bottom of your rational function have different degrees, then it's a really easy choice. If the numerator has a smaller degree and the bottom has the larger degree, then yes, you do have a horizontal asymptote, and that asymptote is the line y equals 0. If you have the reverse, if the top is larger in degree than the bottom, then you do not have a horizontal asymptote. So when the top and bottom have different degrees, it's a very easy calculation. If the bottom has a bigger degree, y equals 0. If the top has the bigger degree, no horizontal asymptote. The only calculation you'll have to do at all is just in the one case where the top and the bottom both have the same degree. So in that one case, you'll need to look at the leading coefficient for the top and the bottom, and your horizontal asymptote would be the line y equals leading coefficient for the top over leading coefficient for the bottom. So let's start with an example here, and this one is super fast because we don't have any factoring that needs to be done. There's also no canceling that needs to be done. So that's telling us a few things. Right away, we can definitely say that there are no holes. And that's because we have one excluded value, and that excluded value, if we're looking at it, would be the excluded value that x cannot be negative 2/3. And of course, the factor that gave us the excluded value certainly is still there. We did not cancel it out or get rid of it in any way, which means that we don't have any holes in our graph, and rather we will have one vertical asymptote, and that will be the line x equals negative 2/3. As far as the horizontal asymptotes go, we do have one. If we're looking at the top and the bottom, they both have degree 1. They both have x to the power of 1 as their highest power of x. And so this is that one special case where we do have to do a little calculation for our horizontal asymptote, and that would be that it's the line y equals leading coefficient for the top over leading coefficient for the bottom. So for this rational function, we have the horizontal asymptote y equals 4/3. All right, another one up here. We've got g of x. This one I have to do a little bit of factoring. Not too difficult to do for this one. It's a nice difference of squares, x minus 3x plus 3. We have our two excluded values, 3 and negative 3. We didn't cancel any factors out, which again means that we'll have no holes in this graph, so no holes. We do have two vertical asymptotes for those two excluded values, so the line x equals 3 will be one of them, and x equals negative 3 will be another one. And as far as horizontal asymptotes go, since the degree of the top is smaller than the degree of the bottom, yes, we do have a horizontal asymptote, and it's the line y equals 0. All right, one more to do. So this one, looking at this, we've got a little bit of factoring to do. Top, I can factor 3x out. Bottom, I'll take a 2x out. And then I can factor the bottom a little further. And I can cancel a few things. The x's cancel from the top and the bottom, and the x minus 3's cancel from the top and the bottom. So for this one, it's a little bit more complicated. Unlike the last two examples, we had 3 excluded values here, 0, 3, and 1. And a couple of those factors we've managed to cancel out completely. The x and the x minus 3 are completely gone, which means that the x equals to 0 and x equals to 3, these are both going to be locations for holes. So we'll have one hole when x is 0. And of course, to find our value for y, we need to put in that 0 for x. So one of the holes in this graph will be at 0, negative 3/2. And the other hole that we'll have in the graph will be when x is equal to 3. And of course, y will be positive 3/4. So the other hole that we have in the graph is the point 3 3/4. Okay, so we've taken care of the holes for this function. We still need to talk about vertical asymptotes and horizontal asymptotes. So as far as the vertical asymptotes go, again, that has to deal with our excluded values. And the only other excluded value that we haven't talked about yet is the excluded value of 1, which came from the factor x minus 1, which is still there after we've simplified our rational function. So that's telling us that x equals 1 is going to be the location of is going to be the equation of a vertical asymptote. Now, as far as the horizontal asymptote goes, one of the nice things about rational functions is that it doesn't really matter whether we look at the simplified version or the unsimplified version. Notice that in each case, the degree of the top happens to be smaller than the degree of the bottom. For the original function, it was degree 2 for the top and degree 3 for the bottom. In our simplified version, it's degree 0 for the top, because it's a constant function, and degree 1 for the bottom. Either way, we draw the same conclusion. Since the bottom has the bigger degree, then yes, we do have a horizontal asymptote, and it will be the line y equals 0. Okay, one last one to do here. This one is in factored form, and so I don't really have a whole lot of work to do. I will just cancel those x minus 1's, giving me 2x plus 1 squared over x plus 1, 3x minus 1. And just again talking about holes in vertical asymptotes first, we know that we have negative 1, positive 1, and positive 1/3, all as excluded values. Now, as far as the positive 1 goes, that came from a factor that got canceled and removed. So that means that we were going to have a hole when x is equal to 1. And of course, if we wanted to know what the y value is, we put the y value into our simplified version of k of x. So I have the point 1 9/4. The other two excluded values, -1 and 1/3, those must be locations for vertical asymptotes. So we have a vertical asymptote x equals -1, and we've got one x equals 1/3. The last thing to talk about here would be the horizontal asymptote. And so for that, again, you can look at either the simplified or the unsimplified version of this function. Either way, though, we're going to need to know what the degree of the top and the degree of the bottom is. And so this is where we use our skill from 5.2 to figure out for the top, the leading term is 2x squared, or in other words, 4x squared. For the bottom, the leading term is x times 3x, or 3x squared. So that means that we have the same degree for the top and the bottom. Degree 2 for the top, degree 2 for the bottom, which means, yes, we do have a horizontal asymptote. They do have the same degree, and that means it will be the line y equals leading coefficient for the top over leading coefficient for the bottom. So the line y equals 4/3 is our horizontal asymptote for k of x. Now, just to set the scene for the last video for this section, when we're graphing rational functions, a lot of what we're going to do is what we just did in the previous video and this one, which is begin thinking about your domain, locating any holes and any vertical asymptotes, plotting those on your graph, finding your horizontal asymptote, plotting it on your graph as well. It also suggests here that if you have a horizontal asymptote, you might want to find any points where the graph crosses the horizontal asymptote, which I think is a nice thing to do if you have lots of extra time. I don't think it's strictly necessary to give you an idea of the shape of the graph. And in a lot of cases, you're going to find that anyhow, just by following all the clues and putting them together, your x-intercepts, your y-intercept, what's happening with the asymptotes, what's happening near the hole, and all the rest. So if you have extra time and want to find that out, then you certainly can. So for example, if I wanted to know, does k of x ever cross the horizontal asymptote of y equals 4/3, I would be wondering, is k of x ever equal to 4/3? I would be solving where is k of x, that expression, equal to 4/3, which is part of the reason why I'm suggesting that's maybe not the best thing to spend your time on. Solving that equation would take a little bit of time, and already graphing a rational function, you'll see, takes quite a bit of time on its own. So that just feels like a little bit of extra work for not much payoff. So you can do that if you want, but you strictly don't have to. You certainly do, though, need to find holes, vertical asymptotes, horizontal asymptotes, plot them all, and also label them all. The other thing that we'll need to do, of course, is find our x-intercepts and our y-intercepts. The y-intercept is always easy enough to find because, remember, for a y-intercept, you just let the x value be 0, and then for the y value, you're just going to put 0 into your function, and that will be how you'll find your y-intercept. As far as the x-intercepts go, this is just using the fact that for any fraction, a fraction is equal to 0 only when the numerator is equal to 0. So if you have f of x is equal to some sort of business over some other sort of business, the x-intercepts will only happen where the numerator is equal to 0. One nice little thing, though, the discussion that we had in 5.3 about x-intercepts and the behavior at x-intercepts based on multiplicity, that still holds here as well, too. So if you were to think about, for example, the last example that we had, at k of x, you can see looking at it that it would have one x-intercept when x is equal to -1/2, and since that comes from a factor with multiplicity 2, you would know that you should be touching the x-axis and not crossing it at x is equal to -1/2. So all that sort of stuff that we did with graphing polynomials and x-intercepts, that still will apply here when we're talking about rational functions as well. So we find our x-intercepts, we find our y-intercepts, we plot those, label them if we need to, and then the last part for graphing a rational function is that we may still need some extra points on top of that. For polynomials, it was kind of easy because, like I said back in 5.2, polynomials are nice and smooth, they have no excluded values, so as long as you know where the x-intercepts are and what's happening at the far ends, whether you're going up or down, that's enough information to plot a polynomial function. But when it comes to graphing a rational function, you may find that you have vertical asymptotes drawn, and you may have horizontal asymptotes drawn, and you may have a single point or two somewhere, but that may mean that you have large chunks of the graph where you just don't really have any information as to what's going on. So you may need to take an extra point in that side of the graph, pick an x value, and find the corresponding y value so you'll have something to plot. And same thing on the other side, you may need to take an extra value and find out what its y value is and plot that as well. Of course, as always, with every point that you take and find its coordinates, you need to plot it and label it. So ideally, you don't want to take too many extra points if you don't need them. For the most part, we'll be able to do our graphing by asking ourselves a question of what if and seeing which option goes well with all of the clues we found and which ones contradict the clues we found. So for example, when we're graphing a rational function and we've got ourselves a vertical asymptote and we've got ourselves a point that we know is on the graph, we'll ask ourselves the question of what happens as we get close to the vertical asymptote. Are we going up or are we going down? And one of those will be impossible, and we'll be able to figure out based on our other clues that we have, other intercepts, other points on the graph, other asymptotes, we'll be able to figure out which is the correct option as for our graph.